Okay, so for this video, we want to look at a continuous random variable where it is conditioned by some event, right? So this is the second part of section 7.1. The first part, in the other video, we cover discrete random variable, which is conditioned by some event. Okay. So here in this video, we looking at x, which is continuous random variable, and we have b, which is some event in some random experiments. So if you look at this line, right, this indicate the range of random variable x. So x, the outcome of x could be between 0 and 10, for example, and event b covers some part of the outcome, right? It's some subset of the whole outcome, right? So that's B is this. So we have a knowledge of event B. We would know that X have to be within this range, right? It's not gonna be uh, anything outside this green area, right? Those the probability of those is event gonna be zero. Okay. So how do we determine CDF of this random variable x given this event b? Okay. So if you recall the CDF or cumulative distribution function of x is the probability that random variable x is less than or equal to some number x. Okay. So with the knowledge of event b, this will change the probability of this event, right, where x is less than or equal to some number x. The way we're going to denote this conditional probability, we're going to use these notations. So P is the probability. It's the probability that random variable x less than or equal to some number x given the condition. The condition is this event B. Now, as you study this conditional probability in the past, you know that this is equal to the probability that x less than or equal to x and given the condition have two holes as well. So that means random variable x must be in this subset B or this set B divided by the the condition, which is the probability of event B. Okay. Now, if you're looking at this conditional probability, this is exactly what we call conditional CDF. So it's the CDF, right? It's probability of x less than or equal to some number x, but there are some conditions. Okay. The way we're gonna denote conditional CDF is we're gonna use capital letter X just like before with the subscript of the random variable x. But the new thing is this: given event B, right? So if we see this, then we know it's conditioned on event B. Now, if we have CDF, that means we can also find the probability density function. And again, this is going to be conditional probability density functions. The way we find conditional probability, the conditional PDF, there are two ways, right? The first way is we can find the PDF by differentiate the CDF. So the CDF is have to be obtained, and then we just differentiate it with respect to x. And the end result, we're gonna get the PDF. Again, the PDF which we're gonna use small case f uh, to denote PDF. Okay, and with this given the condition B. The second way to find the conditional PDF is you take the the regular PDF or the unconditional PDF, right? So this is small case f uh, for the random variable x, and you divide it by the probability of the event of the condition, right, of event B. And this only cover or this is only valid when the outcome is within the set B. Anything outside the set B, that will not happen, right? Because we know that B has to hold or B is true. Anything outside B will not occur. So the density will be equal to zero. Let's take a look at some example. So we have x be a Laplace random variable with the following PDF. So when we say Laplace random variable, it has this kind of PDF, right? So the PDF is 1/2 e to the power minus absolute values of x. And you see here that x or the outcome could be anything between minus infinity and infinity. Okay, so if we plot this PDF functions, right, you get this kind of curve. You see that when x is bigger than 0, right, when x is positive, the PDF is coming down, right, decreasing and getting closer to 0. And when x is negative, right, again, it's most likely that the value is going to be close to 0, and after that, it's going to be less probable, or the probability is coming down, right? The density is coming down. Okay. So let's define event B. So let's see, B is an event that x is greater or equal to 0. That means event B only cover the right half of the outcome, right? The entire right half from 0 to infinity. Okay. So first we're gonna find the probability of this event. So that means we want to find area under the curve, right? From 0 to infinity, because that's what this is, right? When x is bigger or equal to 0. So the PDF is this, right? We want to integrate from 0 to infinity. So the PDF again is 1/2 e to the power minus 6. Well, if you take a look at what we wrote before, isn't it e to the power minus absolute values of x? Why we take off the absolute value? Well, we take off the absolute values because we only consider positive x, right? So you see we integrate from 0 to infinity. So absolute or no absolute, it's gonna be always positive, right? So e to the power minus x, that's enough, right? So we can integrate this, right? We take 1/2 outside, and then we integrate, we get 1/2. So that means the probability of event B occurring is equal to 1/2. But you can see this because this PDF is symmetrical, right? You integrate this area is going to be 1/2, the other half is going to be another 1/2, right? You integrate the entire PDF, you have to get to 1. Okay. Now let's find out conditional CDF, right? Again, right, the conditional CDF is given by the probability of x less than x, right? The the event B, right? Remember, event B is this, right? X has to be greater than 0, divided by the probability of event B. Okay, that probability we already found out, it's equal to 1/2. The probability on the top, you see that x has to be less than this number, small case x, but it has to be bigger than 0, right? We can combine this into this one range, right? One interval. That means the random variable has to be between 0 and some number x. Okay. So how do you find this probability? Well, the way you do it is you use the PDF. So I'm going to use the PDF, integrate from 0 to x. But now if we use x as the variable of integration, that's going to be confusing. So let's say the integrations has the PDF has this variable a, right? Instead of x, we use a. So a. But we integrate from 0 to x, right? So x is some number. And again, we plug in the PDF from before, right? So 2 in front, it's gonna uh, multiply with 1/2, you get 1. Integrate from 0 to x. And again, since this uh, range of integration is only positive, we don't need absolute values of a. So just a, right? So e to the minus a. You integrate this, you get 1 minus e to the power of minus x. Okay? So that means the conditional CDF, it's 1 minus e to the minus x when x is greater or equal to 0. And it's 0 when x is less than 0. Okay? Right? So remember, anything outside the outside event B, that's not going to be occurring, so the probability is going to be equal to 0. Okay, you can find the conditional PDF by differentiate the CDF. So to differentiate 1 minus e to the power minus x, you get e to the power minus x. Okay, integrate 0, you get 0. So you end up with this. Another way of finding the conditional PDF is you take the full PDF, the unconditional PDF, which is this, divided by the probability of event B, which is equal to 1/2, right? This is when X has to be in event B, so X has to be bigger or equal to 0, okay? So you see this divided by 1/2 cancel with one another, okay? And you end up with the same expressions for the conditional PDF, okay? So you can find the conditional CDF first, and then differentiate that to obtain the PDF. That's the first method. Or you can use the unconditional PDF and divide it by the probability of the event or the probability of the conditions, right? That's gonna give you the same answer. Okay. Now the other concept that we want to study is what if the experiments are partitions into m event, right? So let's look at some random variable x. So x is from some experiment, and the outcome of the experiment is between a and b, right? So uh, x random variable is between a and b, and in this range of x, right, there are different events that cover different part of this range of x. Let's say we have small m events that are not intersecting with one another, and also it's cover everything in this range, right? So got we b1, b2, b3, and then bm. Bm is true in this partitions, right? B1 will be true in this partition, for example. So the way this work is, if we want to find the full PDF without any conditions, one way to find out this unconditional uh, PDF is to use the conditional PDF in different event, and then you weight it with the probability of that event, and then you sum this up, right? Basically, you weight conditional PDF with its probability of the event of the conditions, right? And sum everything up. That means if we know the conditional PDF of event condition on B1, you multiply with probability of B1, right? Plus conditional PDF of that condition on B2, right? And multiply with probability of B2 until, right, you do this until you get to the last partition or last event BM. If you do add all this up, you're gonna get back to the full or the unconditional probability. So let's take a look at the example, right? So from previous example, we remember that we looking at Laplace random variable. So the outcome could be the entire real line, right? So let's say B1 is the event where x is bigger or equal to 0. So we have done this before, the joint PDF given B1, right? Or in previous example, we use B, okay? Is equal to e to the power minus x when x is bigger than 0, and 0 when x is less than 0. The probability of the event is equal to 1/2, right? So we done this before. Let's say B2, right? This is another event, which is when x less than 0. Okay, so that means it cover this entire left half of this real line. Okay, so if you look at B1 and B2, this compose the whole outcome of x. Okay, and we can do similar. We can take similar step to find the conditional PDF of condition on B2. This is gonna be equal to e to the power of x. This is when x is less than 0, and 0 when x is bigger or equal to 0, right? So remember this conditions on B2. So anything is, it has to be, x has to be less than 0. And the probability of this event is equal to 1/2. Now, if you want to find the unconditional PDF, then you take the conditional PDF given B1 multiplied with its probability. So this is 1/2. Okay. The joint the conditional PDF given B2 multiplied with the probability of B2. This is another 1/2. Okay. So so conditional PDF given B1. So it's this multiplied with 1/2, right? So we got the first case. This is when x is bigger than 0. 0 divide multiply 1/2, that's going to be 0. Okay, so second case, it's going to be this multiplied with 1/2, right? When x is less than 0. So we got this. This multiplied with 1/2 is going to be 0. So you add this, which is 0, with this, it doesn't change the answer, right? So at the end, we get this. This is the full PDF. Okay. Now if you take a look at this, so when x is bigger than 0, it's e to the minus x. When x is less than 0, it's e to the x, or you can combine this into a single expression, which is 1/2 e to the power minus absolute values of x. Okay, this is when x could be anything positive or negative, and this is the original PDF of Laplace random variable that we are given in the first example.